Okay, this short video is on plotting straight line graphs by hand, and it accompanies another video plotting the same set of data points using graph plotting software, Autograph. So if we look at this data set, this is for the volume of a gas and how it changes with temperature. So the volume is measured in milliliters, and as I increase the temperature from 60 degrees to 85 degrees, you can see that the volume is increasing, and I want to plot a graph of temperature against volume and find the equation of the line, the relationship that describes the volume and the temperature of this gas. If we look at the volume data here, you can see a rather inconvenient numbers, 0.0025. So I'd have to set a scale that starts at least 0.0025 and goes up to 0.0029. I could also have very big numbers like 25,000 or 250,000, something like that. So we need a way of representing these very small or very big numbers. So what we do is we generate another column. So if I were to do this on the right here, where I'm going to change the position of the decimal point to a more convenient place in the volume. So now the volume is going to be in this column, volume. If I change the decimal point 3 places to the right, 1, 2, 3, that makes that 2.5. So if I were to put 2.5 in here, that would be a much more convenient point to plot on a graph. But it really is not 2.5. The decimal point should be 3 places further back. So I should really move the point 1, 2, 3 places backwards to make it 0.0025. So what I need to do is to indicate that by saying that my units now are times 10 to the minus 3 milliliters. So each of these numbers that appears in this column here is actually times 10 to the minus 3. So now I can carry on and do that with all the rest of the numbers. So this next one will be 2.58 times 10 to the minus 3. And so on. 2.66 times 10 to the minus 3. 2.74, 2.82, and 2.9 or 2.90. So now these are much more convenient data points to plot on a graph. And this is an important idea to be able to do this. Of course, this number could be anything. I could have used 10 to the minus 4 and called it 25, 25.8, and so on. But we tend to, in engineering notation anyway, work in multiples of 3. So now I'm going to plot these last 2 columns, the middle column and the right-hand column. Now the question is, which set of data goes on the x-axis, which set of data goes on the y-axis? Well, generally, we put what's called the dependent variable on the x-axis. Which is the dependent variable? Well, if we look at these, the independent variable is one we consider first. That goes on the x-axis. And the independent variable is the one that we control. And if you look at these values here, in this column, they're going up in multiples of 5. So I'm controlling that variable. I'm gradually increasing the temperature of the gas and noting the volume at 5-degree centigrade intervals. So the temperature scale is the one I'm controlling. That's the independent variable, sometimes called a controlling variable, and that's what goes on the x-axis. So that's the independent variable. It's not always obvious, because they don't always go up in nice equal lumps, what the independent variable is, but we try and put the one we're controlling, the independent variable, on the x-axis. Time is often the thing that we're controlling, and so that's often on the x-axis, time. So the y-axis then is the other variable, and that's called a dependent variable because that depends on the independent variable. The size of the volume depends on the temperature, so that's the dependent variable. Now I'm going to plot these values, and so I've got to set my scales. So I've got to set a scale so that I go up to 85 degrees centigrade and up to 2.9 for the volume. If I set my scale so that, and I've put a few on here that I've taken off autograph, but if I were to set my scale at 0 for the temperature scale, going up to 100 degrees in lumps of 20, so that's 80, and so on, and I set my volume scale going up to 2.9 or up to about 3, so that's 0, 1, 2, 3. So this is volume times 10 to the minus 3 milliliters, and this is temperature in degrees centigrade. So don't forget to label the axes. If we start both sets of axes at 0, you can see that all the data is in one corner, which isn't always convenient. All the data is squashed together in one corner. It'd be nice to have those data points further apart. But at least, when I get to put this straight line on, which is what I'm going to do next, put the line of best fit on, when I put my line of best fit on, I can actually see roughly where it cuts the y-axis, because my straight line is going to start here and go through those data points and then just carry on down and try and find out where it cuts the y-axis. If I choose a set of data that or axes rather, so that I can get all the data points in, starting at 2.5, which is where the first data point is, and going up to 3, so this is 2.5 here, going up to 3.0, this again is volume, times 10 to the minus 3 milliliters, and that's temperature in degrees centigrade, starting at 60 and going up to 90. So in other words, I make sure my scales exactly fit the data. The trouble with that is, because my x-axis doesn't go to 0, I can't find the intercept. So I need to set scales so that I can find the y-intercept. So my x-axis needs to start at 0, but my y-axis doesn't need to start at 0. So I need to try and choose a set of scales that will allow me to find the y-intercept, but also spread the data out as much as possible. So if we look at this one here, it looks as though my data points go down to the y-axis, but you might be tempted to think that this actually is a y-intercept, whereas in fact, I plot my data points, comes down here. This isn't the y-intercept because the y-intercept is when this equals 0, and I'm starting at 50 on the x-axis. So I've tried to make my data points convenient, but again, I'm not finding this y-intercept here. So what I need to do is make sure I start at 0 on my x-axis, but I can actually do a more useful scale for the y-axis. I can zoom in on that y-axis a bit to allow me as much as possible to let my data points spread out like this. So now I can come up with a value for the y-intercept. One of the dangers, of course, is that will I hit this line? So if I come down here, I've plotted the points, I've tried to make it as convenient as possible. I come down, drawing a line of best fit, just off the scale. So that's the danger with plotting it by hand. There's not really an answer to that. You maybe will just have to draw rather big scales like this one here, get it as roughly the value, and then say, okay, it's about 1 point something. So let's start my y-axis, my volume, at 1 and plot another graph. So just means you might have to plot more than one graph if you're doing it by hand. Obviously much easier using graph plotting software. So now I need to, well, maybe I've made a mistake here. I could try and extrapolate down. If I've allowed my graph, I might decide I'm going to carry my graph down a bit further and try and guess where it is, or I might decide to plot another graph. So now I've made sure my scale starts at around about 1. So if I plot my line of best fit now, coming down here, obviously you would use a ruler to do this. I can come up with my Y-intercept. So I draw on my line of best fit, going through the data points as well as I can. If there's a particular data point, say there was one here that was off the line, I would ignore that. I'd check to make sure I plotted it properly, and if I'd actually done an experiment for this, I'd go back and check that result, make sure there wasn't an error somewhere. But if all the other data points are lying in a straight line, it might be possible to ignore that one. Maybe give a reason why you're ignoring it. So then I plot my line of best fit on. Now the last step is to find the equation of this line. Well, C turns out to be about that's 1.5, and that's 1.4, 1.3, so about 1.35. And what have I got here? Don't forget I've plotted volume times 10 to the minus 3 milliliters against temperature in degrees centigrade. So this 1.35, don't forget, is times 10 to the minus 3 milliliters. So that's my estimate for the Y-intercept. And now I want an estimate for the gradient. So what I have to do is physically draw on here a right-angled triangle. I try and choose convenient points. So in other words, I'll look for a point where it cuts through convenient points. So that would be a good point to start here. So that's one good place for the y-axis because it cuts through some nice convenient points on the graph. Looking for another convenient point, well, you couldn't go right down to the y-axis if you like, to the 0 on the x-axis rather, but let's just take this point here. So there's my right angle triangle, and now I need to find the length of this line and the length of this line. So that's taken from the data point. So this is 2.5 taken from the graph. This point here on the y-axis is 1.6. So y equals 2.5 minus 1.6, which is 0.9. But don't forget, that's times 10 to the minus 3, because the scale is times 10 to the minus 3. What about the x-axis? Well, this point here is 60. This point here, if that's 20, 10, around about 12. So x equals 60 minus 12, which is 48. So now the gradient m equals y over x, which equals 0.9 times 10 to the minus 3 divided by 48. And put that into a calculator and come up with the value for m. So m equals, on my calculator, well, if I look at the figures I've put in, I've estimated those to about 1 or 2 significant figures, so there's no point writing it to more than 2 significant figures. 1.9 times 10 to the minus 5. In using engineering notation, it's got to be multiples of 3. So if I move it one more place to the right, that will be 0.19 times 10 to the minus 6 to 2 significant figures. And what are the units? So technically I should write m equals 0.9 times 10 to the minus 6. Units are the units for the y-axis, which is milliliters, divided by the units for the x-axis, which is degrees centigrade. So in other words, this gas is increasing its volume at the rate of 0.9 times 10 to the minus 6 milliliters per degree centigrade to 2 significant figures. So I now have the figures for y and c that can go in my equation of a line. So what is the equation of the line? Y equals mx plus c, where y is the dependent variable on the y-axis, which is volume. So this gives volume equals m, which is 0.9 times 10 to the minus 6, times the volume plus c, which turned out to be estimated as 1.35 times 10 to the minus 3. 1.35 times 10 to the minus 3. Okay, so that's that done. You now have a relationship between the volume and the temperature of the gas. Oh, that should be temperature, shouldn't it? Temperature plus 1.35 times 10 to the minus 6.